Okay, I want you to imagine something for a second. What if we could capture literally 100% of the sun's energy? Not just putting solar panels on a roof, but capturing the whole thing. We're talking about enough power to run human civilization not just for another year or another century, but practically forever. No more energy crises, no more fighting over limited terrestrial resources. It sounds totally like science fiction, right? But today, we're going to dive into the actual astrophysics and the mind-blowing engineering behind the ultimate power source, the Dyson sphere. Welcome to The Explainer.
Here's our roadmap for today. We'll start by looking at the ultimate energy solution and then break down the Kardashev scale to see exactly where humanity ranks. After that, we'll do some serious myth-busting in our Dyson sphere versus swarm section, map out the actual engineering of a star megastructure, play cosmic detective in hunting for alien megastructures, and finally, look ahead to humanity's interstellar future.
Section 1. The Ultimate Energy Solution. Earth's Energy Limits.
So as our technological ambitions keep growing, we're talking planet-scale computing, massive AI data centers, and global electrification, we are hitting a wall. We're getting dangerously close to the physical limits of what Earth can actually provide. Take a look at this staggering number, 20 trillion watts. That is roughly humanity's entire global power consumption right now. 20 trillion. It sounds absolutely massive, doesn't it? But here's the crazy part. Our sun puts out billions of times more energy than that. And right now, almost all of it is just radiating uselessly into the dark, empty void of space. If we could tap into just a tiny fraction of that wasted stellar energy, boom, our resource problems would evaporate instantly.
Moving on to Section 2. The Kardashev scale explained, classifying cosmic civilizations.
So, how do we even begin to classify a civilization that's capable of harnessing stellar power? Well, back in 1964, a Soviet astronomer named Nikolai Kardashev came up with this brilliant framework based purely on energy use. He broke it down into 3 types. A Type 1 civilization uses all the available energy on its home planet. That's about 10 to the 16th watts. A Type 2 civilization makes a massive leap, mastering the total energy output of its host star. That bumps the power limit up to an unbelievable 10 to the 26th watts. And then there's Type 3, which commands the energy of an entire galaxy. Do you see that huge jump between Type 1 and Type 2? That Type 2 level is exactly where the concept of a star megastructure actually becomes a reality.
Now you're probably wondering, where do we fit into all this? Later on, the famous astronomer Carl Sagan refined this scale into finer mathematical increments, and, well, prepare to be a little humbled, because humanity currently sits at roughly Type 0.73. Yep, we haven't even mastered the energy of our own planet yet. We're still relying way too heavily on fossil fuels and just barely scratching the surface of our renewable potential. But charting that path toward becoming a Type 2 civilization gives us a really clear, albeit totally daunting, technological goal for our distant future. All right, Section 3. Dyson sphere versus Dyson swarm, myth-busting the megastructure.
The whole idea of capturing a star's energy is super famous today, mostly thanks to physicist Freeman Dyson back in 1960. Fun little side note though, his inspiration actually came from a 1937 sci-fi novel called Star Maker. But look, we really need to separate the science fiction from the science fact here. The most popular image you see in movies, a giant, solid, continuous shell completely enclosing a star, is literally impossible. A rigid shell lacks a gravitational restoring force. That means if it gets nudged by, say, a random meteor, the whole thing would eventually drift and crash right into the sun. Plus, there is absolutely no known material in the universe strong enough to handle the immense structural stress of its own gravity at that insane scale. The actual, astrophysically realistic alternative, the Dyson swarm. Instead of a solid shell, picture a vast, loose cloud of millions, maybe billions, of independent satellites and solar collectors. They'd all be traveling on their own separate, carefully coordinated orbits, working together to capture the star's light.
To clear up this huge, widespread misconception once and for all, let's just listen to the man himself. Freeman Dyson actually wrote, "A solid shell or ring surrounding a star is mechanically impossible. The form of biosphere which I envisage consists of a loose collection or swarm of objects traveling on independent orbits around the star." He was actually pretty bummed out later in life that the whole solid shell idea caught on in popular culture under his name, because his true, scientifically grounded vision was always a dynamic, orbiting swarm.
Which brings us to Section 4, Engineering a Star Megastructure, Blueprint for a Swarm. Okay, let's take this out of the realm of theoretical astrophysics and get into the hard engineering. If humanity actually wanted to build this thing, how on Earth or off Earth would we do it?
Well, here is the mind-boggling construction blueprint. And spoiler alert, it requires quadrillions of tons of material. Step 1, we travel to Mercury. Step 2, we deploy a massive fleet of autonomous robotic miners across the planet's surface. And Step 3, we manufacture these solar collectors and launch them into orbit using massive electromagnetic railguns.
Now, you might be thinking, wait, why Mercury? Well, Mercury is absolutely the most logical first step for gathering our raw materials. First off, it's the closest planet to the Sun, which is exactly where we need our solar collectors to end up anyway. Second, it has no atmosphere. That is huge because it means we don't have to fight atmospheric drag when we're launching stuff into space. Third, its low gravity makes launches way cheaper and easier than from Earth. And finally, its composition is basically an engineer's dream. It's about 70% metal, mostly iron and nickel, and 30% silicate. It's essentially a giant, floating warehouse of building materials. So yeah, we literally have to dismantle an entire planet to build this swarm, but Mercury is practically begging for the job.
Once our robotic fleet autonomously mines all those materials, we have to actually build the collectors. But we wouldn't be building those heavy, fragile solar panels you see on houses today. That's way too inefficient. Instead, we'd manufacture vast, incredibly thin parabolic space mirrors. These mirrors are designed to capture the collimated sunlight and focus it into a super tight, concentrated beam. That energy beam is then directed to specialized orbital energy stations, where it gets converted into usable power.
So how do we get millions of these giant mirrors off Mercury and into orbit around the Sun? We definitely wouldn't use traditional chemical rockets. They just require way too much fuel. It wouldn't make sense. Instead, we'd build massive electromagnetic railguns right on the surface of Mercury. Think about basic physics. The formula for kinetic energy is 1/2 mass times velocity squared. These huge railguns would use pure electricity to accelerate payloads down a massive track, launching the solar collectors at escape velocity. They just fire them directly into their designated solar orbits, day in and day out.
And you know what's really wild? We're actually seeing the very early baby steps of this exact kind of technology today. Sure, a complete Dyson swarm is a long, long way off. But look at our current heavy-lift rockets. We're seeing incredible leaps with vehicles like the Falcon 9, the Falcon Heavy, and especially Starship, which is designed to lift over 100 metric tons to orbit while being completely reusable. These are the foundational tools we need to start moving massive payloads in space. We're actively watching the birth of an off-world industrial economy right now. Section 5. Hunting for Alien Megastructures. The Cosmic Detective Story.
Now, if building a Dyson swarm is the logical next step for advanced civilizations, that means there might be Type 2 civilizations out there right now building these things. And if they are, astronomers might actually be able to detect them from Earth. The key to this cosmic detective hunt is something called infrared waste heat. The laws of thermodynamics are pretty strict. When you capture a star's light and utilize it for energy, some of that energy inevitably has to be radiated away as waste heat. Freeman Dyson actually theorized this. He said, instead of just listening for alien radio signals, we should be searching the galaxy for weird, anomalous sources of infrared radiation. Basically, we're looking for a star that looks artificially dim to our eyes because a megastructure is blocking its visible light, but is blazing incredibly brightly in the infrared spectrum because of all that thermal waste heat.
And this perfectly sets up one of the greatest modern space mysteries, Tabby's star. This is just wild. When astronomers looked at historical photographic plates from 1890 to 1989, they saw that this specific star had inexplicably dimmed by an overall 20%. Then, between 2009 and 2013, the Kepler Space Telescope caught it rapidly dimming by up to 22% in these weird, short, irregular bursts. That is way too much dimming to just be a normal planet passing by. So in 2015, the alien megastructure hypothesis was officially proposed. Were we actually looking at a Dyson swarm under construction right before our eyes? The idea of a real-life alien megastructure completely captured the world's imagination. It made global headlines everywhere. But as more data came in, further scientific observations kind of threw cold water on the whole theory. The big issue? There was a distinct lack of that crucial infrared waste heat we just talked about. Without that heat signature, an alien megastructure is highly unlikely. Today, the most accepted explanation among astronomers is that it was likely a massive swarm of fragmented comets, dust, or planetary debris passing across our line of sight, which naturally creates those bizarre dimming effects. It's a bit of a bummer, I know, but it's a fantastic reminder of how rigorous the scientific method really is.
Finally, Section 6. Humanity's Interstellar Future. Looking ahead.
So, let's take a step back. What is the ultimate purpose of going through all this trouble to harness such immense energy? Think about it.
Once you control the entire output of a star, you effectively become a post-scarcity civilization. You have enough power to run artificial worlds, build computing networks the size of planets, or even launch fleets to spread humanity across the entire galaxy. So I want to leave you with this final provocative thought. Is building a Dyson swarm humanity's inevitable cosmic destiny? Is it just the mandatory next step for our long-term survival? Or does the empty sky suggest that we're truly alone out here in the dark? The whole concept of a Dyson swarm challenges us to look up, to think bigger, and to never stop pushing the boundaries of what is possible. Thanks so much for joining me on this explainer today, and as always, keep your eyes on the stars.